And this is a continuation of the weak acid, strong base case. We had left off, excuse me, at the equivalence point where the hydrolysis reaction was going to govern the pH at the equivalence point. So we know it's not going to be 7, and our prediction is it's going to be greater than 7. So if you notice, we've got OH being produced. And so in order to use the Henderson-Hasselbalch equation, we need a pKa, and we don't have a pKa. But we can certainly get a pKa, or no, we do have a pKa. We don't have a pKb, right? Because the weak acid was what was given. So the pKa was given as 1.8 times 10 to the negative 4th, and that will not work because our ice table is producing OH minus. So the first thing we need to do is find the Kb for this conjugate base. So we're going to do 1 times 10 to the negative 14th, which is the Kw of water, and put it over the 1.8 times 10 to the negative 4th. And so that gives us a Kb of 5.6 times 10 to the negative 11th. So this equilibrium is going to be set to that Kb. So what we get is 5.6 times 10 to the negative 11th is equal to x squared over 0.133. When we get that x, it's going to be equal to OH minus. So we just need to be careful not to think that that's going to give us a pH directly. So the OH minus comes out to 2.73 times 10 to the negative 6. So POH is the negative log of that number, and POH comes out to 5.56, which gives us a pH of 8.44. So as predicted, the pH at the equivalence point is greater than 7 when you have a weak acid with a strong base. Again, it has nothing to do with the strong base. It has everything to do with this conjugate base undergoing hydrolysis, which is just a fancy term for saying it interacts with water. Alright, after this point, we know we've reached the equivalence point. So any point after, when we're still adding base, our strong base is going to be in excess. That's actually going to make it a little bit easier and turn it into more like the strong acid, strong base case, right? Because we know that any strong base that's in excess is just going to fully dissociate into OH minus, and so then we can get a pH. Alright, so to figure out millimoles of base, I'm going to take my volume and multiply it by the concentration of the base. So millimoles of base at this point is 10.20 millimoles. So we only had 10 millimoles of acid. So as far as excess goes, we have excess OH minus of 0.20 millimoles. So to turn that into a concentration, I need to divide by the volume. So the original volume, I've forgotten now, this problem has gone on for so long. So our original volume was 50. So now I've added 25.5, so 75.50 milliliters. So our excess OH minus concentration is 2.7 times 10 to the negative 3rd molar. So that's the OH minus that's present and diluted, right? So we can get a POH from that by doing the negative log of 2.7 times 10 to the negative 3rd. So the POH comes out to 2.57. pH is just 14 minus that, so 11.43. So again, a very small amount of strong base is in excess, and look what it does to the pH. So it went from 8 all the way up to 11.43. Alright, and then the last case, millimoles of base. Now I've added 40 mils. I'm way past the equivalence point. So I've got 16 millimoles of base. The acid was 10, so the excess OH minus is 6 millimoles. Total concentration is 90 milliliters. So the concentration of OH minus is 0.0667 molar. POH minus the log, we get 1.18, So that means a pH of 12.82. Okay. So this is a screencast and the previous screencast that I think it would be great to actually go back and watch again. Once you've gotten all your notes written down, then really just go back and try to follow it, because the hardest part is knowing what am I doing, in the sense that, at the equivalence point, you need to think hydrolysis. At the midpoint, pH is equal to pKa. Once you've passed the equivalence point, then your strong is in excess, and then it's really just a dilution problem. But getting practice, because what students do is they don't know where to begin. And so if you go back and just watch this screencast again, I certainly think that'll help. So practice 13 is certainly not as many calculations. I wanted to model, adding small amounts of base so that you could see how the pH changes. This is a little bit different. They give you 20 milliliters of your weak acid, and they're saying that they're adding it in the strong base in 5 milliliter volumes. And they give you the pKa for HF, and they've also given you the Ka, which is nice because you've got that handy. So let's go through this rather quickly and just see how this one works. So it says the initial pH, and so the thing that's present is the HF. So it's going to break up, right? We've got 0.20 molar, 0 and 0, up by x, down by x. Okay, so they gave me the Ka, 3.5 times 10 to the negative fourth equals x squared over 0.2. Again, this is really 0.2 minus x, but because of that k, we can assume that this is pretty much going to stay 0.2. So x, when we get it, is going to be equal to the H plus concentration, and that's 8.4 times 10 to the negative third molar. So the pH is the negative log of that, and we get a pH of 2.08. So again, stop and ask yourself, does that make sense? It's an acid, better be less than 7, so 2.8 is a nice starting point. Alright, then they ask, well, how much KOH must be added to reach the equivalence point? So you say to yourself, okay, at the equivalence point, moles of acid equal moles of base. So I need to know how many moles of acid I have, or millimoles. So millimoles of acid is 20 times 0.20, so millimoles of acid is 4. So that means millimoles of base required would also be 4, right? So if I need 4 millimoles, and I know the concentration is 0.10, then I can certainly solve for the total volume. So I want 4 millimoles, and I'm solving for V, which will be in milliliters. So multiply both sides by V, divide by 0.1, V comes out to 40 milliliters. So we would need 40 milliliters of base in order to reach the equivalence point. And then it says, well, what would the pH be at the equivalence point? Okay, say to yourself, this is a weak acid with a strong base. The pH at the equivalence point is governed by the hydrolysis of the conjugate base. Okay, so who's the conjugate base? F minus. What does hydrolysis mean? Fancy word for saying he's interacting with water. So he's going to take on a proton, form back HF, and then OH minus will be left. So we need to know how much of this F minus was produced. Well, if we had 4 millimoles of acid, at the equivalence point we know all 4 millimoles is going to be used up. In the process, how much F minus is going to be produced? 4 millimoles. So if I wanted to find the concentration of F minus, I would do 4 millimoles over the total volume. So I know I have 40 milliliters of base at the equivalence point, 20 milliliters of acid, so I'm going to divide it by 60 milliliters. So my F minus concentration is 0.067 molar. So 0.067 molar, 0 and 0, up by x, down by x, 0.067. Okay, again, I've got an OH minus. I've got a Ka. OH minus and Kas do not go together. So what do I need to solve for? I need that Kb. So I do Kw over Ka, and Kb comes out to 2.9 times 10 to the negative 11th. So now this is my equilibrium. I can set it equal to that K. So 2.9 times 10 to the negative 11th is x squared over 0.067. When I get x, it's OH minus, not an H plus. That's why I want to see these equations written out so you don't screw up and think it's the wrong thing. OH minus comes out to 1.39 times 10 to the negative 6 molar. So the POH is the negative log of that. POH comes out to 5.86. pH comes out to 8.14. Again, before you move on, stop and say, does that make sense? Weak acid, strong base. pH should be greater than 7 at the equivalence point. 8 is greater than 7, so we're in good shape.